So in this video today, we're going to be looking at the relationship or showing that or proving the relationship e to the ix is equal to cosine x plus I sine x. So this is done through power series. We're going to first look at the power series for e to the x. So e to the x can be written as 1 plus x squared by 2 factorial plus x cubed by 3 factorial. And that is just the infinite series from n equals 0, x to the n by n factorial. And that can be shown through Maclaurin series or Taylor series. You can expand that about x equals 0 to find that. I won't be doing that in this video though. And what we can then do is we were looking at e to the ix, so we can sub that in. So what we're doing is we're subbing in ix for x. So we're going to be looking at the infinite sum of ix to the n by n factorial. Now, let's take a look at what that's going to look like. So we're going to have e to the ix equals 1 plus ix plus I squared x squared by 2 factorial plus I cubed by x cubed 3 factorial plus I to the 4 x to the 4 by 4 factorial and so on. Now, by definition, I is equal to root minus 1. I squared is equal to minus 1. So what is I cubed going to be? Well, I cubed is just going to be I squared I, which is minus I. And I to the 4 is just going to be I squared, which is equal to 1. Minus 1 times 1. So we can then apply that to this bit here. So we can say that e to the ix is equal to 1 plus ix minus x squared by 2 factorial minus I x cubed by 3 factorial plus x to the 4 by 4 factorial and so on. And then what we can do is we can see that there's some parts here that have no imaginary terms, i.e. these ones here, the even powers, and the odd powers happen to have the imaginary number in front of them. So we can rearrange this. Let's rearrange this. So we said that even powers had no imaginary part to them. So we can say 1 minus x squared by 2 factorial plus x to the 4 by 4 factorial and so on. Put that in a wee bracket. And then we have the imaginary bit, which was ix minus ix cubed by 3 factorial, and we said it was odd powers, so ix to the 5 by 5 factorial, and so on. And we can bring that I out, so we've got e to the ix equals 1 minus x squared by 2 factorial plus x to the 4 by 4 factorial plus I x minus x cubed by 3 factorial plus x to the 5 by 5 factorial. And these are just the series expansions for cosine and sine. So that's obviously going to be e to the ix equals the sum n equals 0 of minus 1 to the n, as it obviously alternates, and n0 is going to be 1, minus 1 is minus 1, and so on. So we're going to have x to the 2n by 2n factorial, which is cosine, plus I, and the infinite sum of minus 1 to the n, x to the 2n plus 1 by 2n plus 1 factorial. And that is just the same as cosine x plus I sine x, which is what we were trying to prove. Now, an extension of this is a result that many mathematicians and scientists obsess over, and that is e to the I pi plus 1 equals 0. So we're going to be seeing how you get that. So prior to this, you might be wondering, how do you find e to the I pi? So obviously, there's no way to calculate that. We've got two irrational numbers and an imaginary number, so it might seem very difficult to compute this. But with our new result, cosine x plus I sine x, we can just sub in. So this is going to be cosine pi plus I sine pi. And sine pi is just 0. If we take a look at the sine function, so there's pi there on the sine function. And if we look at the cosine function, there's pi there, and that's minus 1. So we can sub that in, minus 1 plus 0, and rearranging, we get e to the I of pi plus 1 equals 0. Now, this is obviously a really, really interesting result, as it's associating really key fundamental numbers and concepts in maths. So we've got 1 and 0, we've got the 0 number, which is obviously nothing. It's like, it used to be pretty a revolutionary idea, easy for me to say, in mathematics, and 1, which is the fundamental number for anything. And then we've got interesting constants, e and pi, which show up everywhere in maths. And not only that, we have I, the imaginary number. So it's a really profound result. And that is